Hello again, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, Unit P3 Waves. And today is the final lesson in the unit, and we're looking at communications. So I want to describe how parts of the electromagnetic spectrum are used for communications and differentiate between a digital and analog signal. And a lot of stuff we're doing today, especially with learning objective 1, will be consolidation of what we looked at previously in the electromagnetic spectrum. So radio waves. First of all, they're used in radios, pretty obviously, television, and they're also used in Bluetooth. So short wavelength radio waves carry more information but over a smaller distance, whereas long wavelength radio waves carry less information but over a larger distance. So Bluetooth, for example, is very short wavelength radio waves, so they can send a lot of information but over not a very far distance. You're looking at tens of meters roughly, and if there's a wall between, maybe less than that even, and if there's a wall between you and the object sending the Bluetooth signal, you probably get some loss of signal there. So if we look at the radio waves here, a transmitter sends out radio waves through the air. The radio waves are absorbed by the receiver here. The electrons in the receiver vibrate at the same frequency as the radio waves. This produces an AC signal in the receiver. Okay, so quick question. Given the Earth is curved, how do you send signals around the Earth? So we can use radio waves to send signal a very long distance, but with the Earth not being straight, with it being curved, it can't just be sent in a straight line. So this is how we do it. We've got something called the ionosphere here, the edge of the Earth's atmosphere. And we send a signal here from the transmitter. It hits the ionosphere. Now, it can't penetrate the ionosphere, so it bounces back off, reflected back off the Earth, etc., until it reaches the receiver. And radio wave transmission here again, put the same slide on twice, I think, for some reason. So some radio waves reflect off the ionosphere to travel long distance. FM and TV signals are not reflected off the ionosphere, so the transmitter must be in line of sight of the receiver. Okay, so FM, frequency modulation, doesn't reflect off the ionosphere, so it has to be fairly close. An FM signal, you're looking at the tens of kilometers sort of range, approximately. Okay, so here's some questions for you to have a go at. Just these ones here on the left, or just these ones to the right. And there's a little extension question there as well. Okay, and I'll put the answer on. I'm not going to talk through, I'm just going to put the answers on. The extension, maybe make a note, take a screenshot, and maybe come back to this later, because I will come back to that one with you a little bit later. Okay, microwaves. Microwaves have a frequency above 3,000 megahertz. Remember, mega is million, not times 10 to the 6, and passes straight through the ionosphere. So microwaves, or UHF, which is ultra-high frequency radio waves, are used in phones, as they don't reflect off the ionosphere. How can you talk to someone on the other side of the world? Well, for this, we need a satellite in the sky. So I'm making a phone call, and I'm phoning Bob. The signal goes from me to this here, and then it sends the signal up to the satellite, which then sends it back to another station, and then to my friend Bob here. So most mobiles are cell phones and use ultra-high frequency and transmit signal via an antenna. However, these are a different kind of phone here. Now, how much do you think this costs? Well, I looked this up about 5 years ago, so the price might have changed, but you're looking at well over £1,000, or in Malaysia, For example, that's about 6,000 ringgit. So why is it so expensive? It's because it's a satellite phone, and you're going to get better reception with it. So the way it works is it bypasses the antenna here. I send my signal straight to the satellite and then send it straight to Bob. So satellite phones use microwaves which penetrate the ionosphere and use a satellite to transmit a signal. Okay. So we need to know a little bit about satellites. So there's two main ones we're going to look at. The first one being, well, the one we're going to look at, sorry, is the first one, sorry, is a geostationary satellite. So the orbit above the Earth's equator. The orbit of the satellite is 24 hours, so the same speed as Earth. Has an orbit of 36,000 kilometers above the Earth's surface, much higher than polar satellites, which we'll look at in a moment. They're used for radio and satellite television, such as Astro, around the world due to its high orbit. And they're always above the same place. So here, this satellite, wait a minute, I didn't quite catch where that was. Looks like it's above somewhere in Southern America, I think. I'm not a geographer. And it'll constantly be above that region because it follows the Earth's orbit. So it's got a period going around the Earth of about 24 hours. Now, we've also got polar low orbit satellites. They go from north to south. These orbits much lower than the geostationary satellites at around 200 kilometers above sea level. They are used in satellite phones, also used for monitoring the weather, military applications, and taking images of the Earth's surface. So one advantage is the short time delay, clear signal and images. The disadvantage is you require more than one satellite for continuous operation. Because, for example, if I'm somewhere here, I can only use this satellite when it's somewhere above me. Okay, so you need quite a few of these. Having said that, though, these few of these, or several of these, will cover the entire Earth. Whereas if I've got the geostationary satellites, they will only cover the areas here above. We also use optical fibers for communication. So you can see here we use light. It's used in Wi-Fi, and this is also more not a communications example, but it is used for Christmas trees. And we covered this earlier on in the unit, optical fiber use. So fibers are thin cables. They're usually used to transmit infrared or visible light. They have a higher frequency than microwaves or radio waves, so can transmit more data. And you've got your core here, so that's the bit where the signal travels down, and there's cladding on the outside, which basically helps it reflect the signal all the way down the cable or the fiber. So even when it is bent, the cables are designed to still transmit data. Optical fibers transmit data using TIR, total internal reflection. The angle of incidence is the same as the angle of reflection. Again, look back at my previous lesson on total internal reflection for more information on that. Okay, now have a go at these questions on the right. I'll include this bit here as well. And again, I'm just going to put the answer on now. Okay, moving on. That's the first learning objective, sorry, complete. The second one now is differentiate between a digital and analog signal. And this here is an example of an analog and digital signal. Analog signals vary continuously. They can take any value, whereas a digital signal has got two possible values, high or low, usually 1 or 0. Whereas this could be, say, for example, 1 here, 0.5, 0.25, 0, minus 0.2, etc. Can have any value, whereas digital is 1 or 0, on, off. So an example here of converting a signal. So you've got an analog signal here. So this is somebody singing into a microphone, picks up the sound of different frequencies and amplitudes and turns it into an analog signal. You've got an analog to ADC, which is analog to digital converter, and DAC is digital to analog converter. The analog signal gets fed into an analog to digital converter, which converts the analog signal into a digital one. A digital signal is transmitted until it arrives at a digital to analog converter, which converts it back to an analog signal. The analog signal is read by a speaker, which reproduces the original sound. So the advantage of transmitting using digital signals, it can be regenerated, so there's less noise. So noise is just unwanted sound, basically, a sort of background sound. Due to, pardon me, accurate signal array generation, the digital signals can be sent further than the range of analog. Digital signals enable an increased rate of transmission of data compared to analog. So basically, it's more accurate, larger range, and a faster speed. Okay, so here is a question for you to have a go at. I will, again, as usual, just pause it. I'll put the answer on the screen in a moment. Okay, and here is an example answer for that question. Okay, let's have a look at some paper 2 questions on both of today's learning objectives, describing how parts of the EM spectrum are used for communication and differentiate between analog and digital signal. A transmitter broadcasts at a frequency of 200 kilohertz. What is the wavelength of these radio waves? So you need to remember that the speed is the speed of light, 3 by 10 to the 8 meters per second. V equals F lambda. So we want to rearrange to get lambda equals V over F. So 3 by 10 to the 8 divided by 200 times 10 to the 3, which gives you 1.5 by 10 to the 3. Optical fibers are used to transmit signals using infrared radiation. The average refractive index for the fibers is 1.5, which row describes a digital signal and gives the best speed information, of infrared radiation in the fibers. So we'll look at the speed first. So it's got refractive index of 1.5. That means it travels 1.5 times slower in the cable. So it's 3 by 10 to the 8 meters per second divided by 1.5, which gives me 2 by 10 to the 8. So it's either A or C. And a digital signal, a signal that consists of only 2 values, or a signal that consists of a continuous range of values. Well, a continuous range of values is an analog signal, so the answer is A. And, pardon me, television station transmits a signal to a television receiving dish. The television has an on-off indicator light. The television is switched on by a remote control, which changes the indicator of the light from red to green. Which EM wave used in these actions has the longest wavelength? So remember the order of the electromagnetic spectrum, again, that's from previous learning. The one with the longest wavelength is the same as the one with the shortest frequency or smallest frequency, which is radio waves. So radio waves are being used here from the TV station to the satellite A. Okay, next question. A large hill blocks the direct path between a transmitter of a radio wave and a receiver as shown. The receiver picks up the signal from the transmitter even though the radio waves do not travel through the hill. Which row is correct? Pardon me. The possible way for this to happen is, well, it's not going to refract, so that would have to go through the hill. Diffraction happens at the edge of a wave, meaning it could refract down. And a stronger signal is received using longer wavelengths, because the longer wavelengths will be diffracted more. Okay, so the next unit, so that's it for today's lesson. The next unit will be electricity and magnetism, which I'll be uploading slowly over the coming months. Thank you very much, everyone, and I will see you in the next unit.